Hey everyone, in this video let's take a look at question 403 frog jump on Leetcode. This is part of our blind 75 playlist on Leetcode where we go through the blind 75 questions. So let's begin. In this question, a frog is crossing a river and the river is divided into some number of units. At each unit there may or may not exist a stone. The frog can jump on a stone, but it must not jump into the water. Given a list of stones' positions in units, which is sorted in ascending order, we want to determine if the frog can cross the river by landing on the last stone. Initially, the frog is on the first stone and assumes the first jump must be 1 unit. If the frog's last jump was k units, then the next jump must be either k minus 1, k, or k plus 1 units. The frog can only jump in the forward direction. Okay, let's take a look at the examples here to see if we can quantify what they're saying here. So looks like what we have is we have a bunch of stones here, and I would just label these stone 1, 2, 3, 4, 5, 6, 7, and then stone 8. And we can see this is kind of like the distance, right? This is like the distance away. So for example, here we have like the start, and then you have stone 1, and then you don't have anything, and then like you have the third stone, and then you don't have anything, and then you have like the fifth stone, etc., right? So it's kind of like that. So what do we have here? So we have that the frog can jump onto the last stone, which is stone number 17, or not number 17, it's technically the 8th stone, but it's a distance 17 away, right? So think of it like that. So the frog can jump onto the last stone by jumping 1 unit to the second stone, right? So it can arrive here to the second stone because we have a stone here, and then 2 units to the third stone. So we'll skip this one and we'll arrive here, which is the third stone, and then 2 units to the fourth stone. And again, we'll skip this and we'll arrive here, go to the fourth stone here, right? Which is, again, look how we're skipping a stone here. So we go to the fourth stone, and then 3 units to the sixth stone. So we will skip this one actually, and then we will go directly here. So it looks like from here, we have another stone here. We have 5, we have 6, right? And then we don't have anything, and then we have don't have anything, and then we have 8, right? So it's like that. So directly from here, or let me see if I did that right. So it looks like we have the start, and then we have stone number 1, which is here. Then we don't have a second stone. We have a third stone. We don't have a fourth stone. We have a fifth stone. We have a sixth stone. We don't have a seventh stone, and we have an eighth stone. So basically, from this stone over here, it looks like it's jumping. How many units? It's jumping 3 units to the sixth one. So it's jumping 1, 2, and arriving over here, right? So we have that. And similarly, we can jump 4th units to the 7th stone. So we go over here. And then we can jump 5 units to the 8th stone. So we arrive finally at our last stone, which is stone 17, with the value of 17, which is the 8th stone from basically what the frog starts off. So in this case, we would return true. Now, in the second case here, we'd return false, and the reason is because it looks like there is no way to jump to the last stone, as the gap between the 5th and 6th stone is very large. It's too large. So what does that mean? Between the 5th and the 6th stone, it's like a 4 gap, right? It's a 4 gap. You would need k equal to 4 here. Now, if we arrive at this position, there's basically no way we can get k equals 4. Even if from like here, we jump directly to here, which means k is equal to 2, the maximum we could do is k plus 1 as 3. So we can't arrive on stone 8. We would arrive on stone with the number of 7, which doesn't exist here. So in that case, it doesn't exist. Okay, so that's the question. And kind of let's see like how we can approach this, right? So given any single position k, it looks like we have a couple of positions to consider, right? We have k minus 1, we have k, or we have k plus 1 units. So when I look at this, I basically just think of, okay, maybe k minus 1 would lead us to the answer. Maybe k would lead us to the answer. Maybe k plus 1 would also lead us to the answer. So we could maybe consider it in terms of like that. So a scenario where we use recursion and to arrive at the answer. So maybe let's start off with a recursive approach to begin this with, and then we can see if we can somehow improve this. So let's see. So first thing we notice is that stones, the first element must be 0, and it must have like 2 elements minimum. So given that the first element must be 0 and that our initial jump is just 1, we would require that these first 2 elements have to be like 0 and 1, right? So we can actually just check that. So if stones 0 to 2 does not equal 0, 1. So if it doesn't equal this, then we're automatically false, right? And I guess the easier way to actually say this is if stones at 1 doesn't equal 1, then we'll just return false automatically, right? Now we don't have to check stones as 0 because it's guaranteed to be 0. Otherwise, let's just have our helper function here, right? Okay, so what do we need in the helper function? Well, I guess one thing we need is the stones, right? We actually need the stones themselves. Now we need to know like which stone we're currently on, because maybe we're on this stone. Well, we need to know where the stone is. Now, we could usually pass in the index, right? You might say this is like index I or whatever, but in this case, index isn't really helpful because you can see here that like all of these are different. All of these are in ascending order. So we can just use like the value itself, like the actual value of the stone, which is like stone with number 3. So we can do something like stone number here, right? So that's that, stone number. Okay, so what are some other things we need? Well, we would need to know K, right? We would need to know, for example, if I'm on stone with the number of 3, then I must have come here from either like stone 1 or maybe stone 2 with K equal to whatever, right? So I need to know like what that K was. So I will pass in K here as well. And I guess one other thing we need to know is like what the last stone is, right? We need to know what the last stone is so we know like where we want to finish off. So I guess we can just calculate that from stone, so we don't really need to pass it into the helper. So let's just begin here. So I guess the first thing we can do here is define our base cases. But before that, when we are doing a recursion, we can pass in something like, let's say we're on stone 3, right? We'll pass in 3, and then maybe we can pass in k as like k plus 1. So given that we have like the stone number, that would be the previous stone number. So we need to essentially calculate the stone number that's new based on k. So we can do something like new stone number is just stone number plus equals k, right? So this will be the new stone number. Now, we can define our base conditions. So what are some base conditions? Well, first of all, something we should check is that if we are at the last stone, then that's true. So we can check if stone number is equal to stones at -1, and this will be the last stone number. In this case, it's true, right? What's a false case? Well, let's say we're like over here, and we make a jump of like 3 units. Well, in this case, we'll be like past the last stone, right? So we don't want that. So we can also check like if stone number is greater than stones at -1, then we can also return false here. What's another case? Well, let's say we're here at stone with the value of 4 and we make a jump of 1. But then we would arrive at a stone of value 5, but it does not exist. So obviously that's an invalid case too. You'll go in the water. So we can check also if stone number not in stones, then we would return false, right? So these are kind of like our base conditions here that we need to check out for. Now, if we have this, all we need to do now is recurse. So we can do something like less, and this will be self.helper. I will fill these in after I define my 3 variables here. So we'll have less, we will have same, we will have more, right? And then basically here, I need to pass in k here. So this will be k minus 1. This would be k. This would be k plus 1. And then I just return whether any of these succeeded, right? That's all I need to return. If any of them succeeded, then I'm happy with my answer. Now, what's one more thing we need to pass in is actually the values into the recursive function. So we have stones, stone number. So what are we starting off at? Well, they mentioned here we're starting off at stone kind of 0, right? We're starting off at stone 0 here. So we'll pass in 0. Initially, k would just be equal to 1 because we can only take one jump here. So then stone num will be equal to 1. And then we will do our calls here where we pass in stone num as 1, but then we either try to go just 1 spot forward, try to go 2 spots forward, or this one, we actually remain in the same spot. So this is actually not allowed. We need to only move forward. So I will just add a condition here. So if k is greater than 1, then I will consider less to be this. Otherwise, I would default less to just be false, right? So we'll do this. And basically from there, if with any luck, if we arrive at the goal, we will return that. And so we can try this and we can go ahead and submit it. And we can see that this one is a working solution. Only problem is that it will take too long. And even with added memoization, it's still going to take longer than we wanted. So I'm not going to add memoization in this video. I have other ones where I've done that, so I'm not going to show it. But basically, you would define a memo here as in the dictionary, and then you would have to basically cache the stone number and k, because these two are the ones that are basically changing, right? So you'd have to cache that information. Okay, so given that we know that this works, well, what's a simpler way that we can do it without this recursion? And maybe if you kind of think about it, what we're really doing is we're starting off at 1 stone here, and we're basically just going outward, right? Like we're considering k plus 1, we're considering k, and we're considering like k minus 1. So basically like at any position, like we're considering 3 more positions that we can possibly go to. So this is basically just hinting at me that we can do a breadth first search, right? Because we're just expanding outwards. We have more than one choice in this case. In breadth first search, you often just have like one choice, but or maybe you have more. Maybe you're going like all four directions, but you're basically just expanding outwards, right? So we can do that in this case. So why don't we try a breadth first search approach? So breadth first search, hopefully, is like very similar to this one, and it turns out it is because once you have a recursive approach, then breadth first search is pretty simple. So let's go ahead and comment this out. In a breadth first search, we need to define our queue, right? We need to define our scene variable. So this is our basically set of visited places. So this will define like the places we visited. And then we will just start off with the queue, right? Now, what are the things we need to add in the queue? Well, we already have that information here, right? What's changing? It looks like stone number is changing and also K is also changing. So we can just pass in stone number and K into the queue, and we will pop that from the start of the queue. So now we have the information that we need. And now we can just check our base conditions. So if stone number is equal to basically the last one, so stones at -1, now we can just return true. Now, these two conditions here, we can basically just check them when we're adding to the queue. We don't want to really check them here. It's because you're going to be adding when you don't really need to be doing that. So we can maybe just skip those. One other thing we can do is, let's say, we can check whether for neighbor in k-1, k, or k+1, right? So these are a set of neighbors. These are the set of locations that we can visit. Well, what do we want to do? We want to calculate the next position, right? We want to calculate what the new position should be. So this one we can say next position is stone number plus k. Now, we don't really have to do this here. We can basically just add it in the queue, but I just kind of want to show both approaches. So here we're just doing the second approach where we put it inside of the queue here. And so now we have our next position and we have k. So we don't need to do this addition here. So now before we add it into the queue, what are some conditions we want to check? Well, I guess first thing we want to check is we want to make sure that this is part of the stones, right? So we can check if next position in stones, right? What's something else we need to check? Well, another thing we need to check is that we haven't visited this place before, because it's possible that if we're over here, right? Let's say this is a new iteration, like let's say we're on this iteration here, this one right here. It's possible that this one will also add in this right here, right? It's possible that it can add in this as well. So we don't want to do that because we've already visited it. So what we can do is we can do and next position k not in scene, right? And again, we have to add in two things because these are the two things that are changing. So if both of these conditions are basically valid, then we can go and add it to our queue. And as with normal breadth first search, we have to add it to the scene right here. We add in next position and then k. Okay, and that's basically it. And then we'll return false over here if this doesn't work. Now, you may ask, what do we need to start off here? Well, we know here we need to start off with the stone number and we need to start off with k. And you can actually see here that we already consider the case where stones at 1 does not equal 1. So we already know that it's 1. So we can maybe just start off at the stone 1. And if we start off at the stone 1, then the k has to be 1, right? Because we came from stone 0 and we took one jump. So the k has to be 1 here. So we can go ahead and we can go with that. And so in this case, if you think about it, k-1, this one basically would require us to go backwards, right? So potentially we can also just check if next position, let's see, is less than stone number, then we just don't consider this one. So we can do that. So now let's go ahead and run our test cases. And it does not work. So let's see where we messed up here. So we have, minimize this. So we have this condition, which is true. We start off here, which is true. We do stone number and k, and we pop from the front, which is true. If stone number is the last one, then it's also true. What else do we need to check? So we have k-1, k, and then k+1. Then we add it. We check if next position is less than, or I guess equal as well, right? Because equal shouldn't work. So I guess the only way is like equal, right? Because k will be positive, so you can't really fall into that approach there. So we'll try this out. Okay, so that was one bug, but it wasn't the bug you're looking for. So we have that. And then here, if next position in stone and next position k not in scene, So I believe that should be correct. So next position in stone and next position not in scene. Here's the problem. So it shouldn't be K, it should be neighbor, right? Because our K is varying. So here it should actually again be neighbor. So that is the problem. So let's try now. And here actually I got to add in neighbor as well. Neighbor, neighbor. So let's try now. Okay, and let's submit. Perfect. So this is a working approach. It's not the best approach, I will admit that. There is like a better one, but I think this one, if you can even come up with this one, like a breadth first search approach, you will probably just pass the question. Other ways you can kind of improve it, instead of using Q, you can use DQ, which is like a constant time removal from the front. Obviously, this one is not like that. Something else you could basically do is convert this to a set, right? Let's actually maybe just do that. So because we're checking if in stones, if stones is like very large, it might take a while. So something we could do is we could just cache last stone as stones at -1, and then we can maybe just convert stones into a set, right? So here we would just do last stone, and then where are we looking at stones again? So stones here. So yeah, so this one should be fine. So let's try this out. And you can see it's much faster. So changing from a list to a set really made a difference over there. Okay, thank you for watching.